Welcome back. So last part, what we were discussing was on the paleoseismic evidence, and as I have been emphasizing right from the beginning, that we'll be interested looking at the evidence or the signatures on fault and off fault. This is one point, and the second important point is that we will be looking at on surface and near subsurface. Okay, that is your stratigraphic sections we will be trying to look at. So both this evidence or the signatures from both this part will help us in identifying of the co-seismic deformation as well as what will be the post-seismic deformation on fault and off fault. So the second part, what we stopped was on the secondary structures, and the secondary structures are mostly we see because of the strong ground shaking, and this can happen far away, more than 100 kilometers away. Any site is located from the epicentral area. So even though the earthquake is occurring far away in like areas like Himalayas, okay, the regions like Indo-Gangetic Plain will get affected. Okay, that is due to the secondary effect. Okay. And this is, as I have mentioning, because of the seismic shaking. So geomorphic expressions, what you will see in terms of on the surface, we'll see landslides, sand boils or sand blows, okay, lateral spreads and all that. These are most common phenomena. And then, but the site wherever this uh, features will be seen should be ideal in a sense, because it has to be water saturated and all that. So that part we will discuss when we are talking about the uh, liquefaction and all that. So one was this geomorphic expressions, and then another is again the stratigraphic expressions, okay, or stratigraphic records we will see. So mostly what we do is that we open up trenches uh, and excavate the trench and then try to see the stratigraphic records if that area is having any signature which is preserved related to this strong ground shaking. Okay. Let us move ahead in this part slowly, and then what we'll see, we learn, and what are the important steps we should follow. Okay. Before going to that, as like uh, the strong ground shaking, for example, I gave in like example of Himalaya, but if suppose this type of earthquake is occurring in subduction zone when you have close by ocean and coastal landforms, okay, then in that case you will see deposits what we call turbidites. Okay. Now coming to the lab and field technique in active fault and paleoseismic studies. Okay. This is the most important part, because this will be the how we will move. Okay. Now immediately after this, I'll be uh, talking about some geomorphic markers. We'll talk about the what are the landforms and how how those landforms can be differentiated from normal processes, that is what we call depositional erosional processes, and if those landforms were formed because of the influence of the climatic variations or they were formed because of tectonic deformation. So those things we will learn in geomorphic markers. But first, what usually the steps or the we follow, the methodology we follow for identifying the active fault and paleoseismic studies to look for the signatures of ancient earthquakes preserved on surface as well as in the stratigraphic records. Okay, so paleoseismic field investigations usually. So before this, basically we take help for using satellite data and all that. That we will be talking very soon. Okay. Now paleoseismic events, that is in paleo earthquakes or ancient earthquakes, okay, can be studied by landform analysis or stratigraphic expression. And mainly we are uh, interested and will be confined to this what we call as the uh, quaternary period only. So we usually do both, and it is ideal to do both because that will give you a complete full handle on the scale and all that. Okay. And then the sequence of investigation initiates from regional scale. So we tried to look at, in the broader sense, what we have learned in this course also, that we have started with plate tectonics. Okay. Then we have come down to the local scale, that is Himalayan tectonics, and then you can go at more narrower side, that is your scale, side scale. Okay, so we do that type of studies in detail. Okay, so investigation often require trenching because we need to see uh, the the preservation of this deformation in sections. Okay, so trenching is must actually. We cannot skip that, and because that provides the data not only on the past earthquake sequence but also we it helps in identifying the recurrence. If we see more than 2 events or 3 events, then we can at least talk about the recurrence interval in that region, okay, on that particular fault. Careful geomorphic study is required before trench excavation, and that is proper establishment of the quaternary stratigraphic landforms. Okay, so stratigraphy of landforms, that also we will learn, but in short, what we see that whether the how the landforms will be classified, older, younger, and so on. Okay, as we do in the stratigraphy sections. Okay, stratigraphic sequence, what we see is that the bottom one is the older deposits, then over that overlying deposits are the younger ones. Okay. Similarly, here also we see that which are the older landscape or the landforms and the younger landform. Okay. The reason identifying older and younger and making this sequence is important because that will tell you that how long the fault has remained active. If the fault has displaced the older landforms as well as the younger landforms, then easily we can say that the fault has remained active since past so many years. Okay, so for that it is important to first have a complete understanding of the landscape. That is what we call geomorphic studies. Okay, so geomorphology of or the morphology of the area has to be studied in detail before we go for even field as well as for trenching. Okay, that is paleoseismic studies for paleoseismic studies. Now, identification of the area. So we identify the area, and since we are going to deal with the earthquakes only, it is always ideal and suggested that you look for literature, uh, historical data which talks about or which has recorded somewhere and we have written records of the historical earthquakes or not. Okay, so that is important because that will give you an idea that what sort of damage was experienced at that point of time during that earthquake. Of course, the population was too less, so sometime you will underestimate, but that is still it is important to have that. Okay, because if it would have been massive earthquake, then it might have been recorded at number of places covering wider areas. Okay, now broad understanding of geological structure is also important. You look at that what we were discussing in the previous slide, that is local tectonics. Okay, then regional and site specific studies, again this is the more or less similar. What we look in the tectonics context, the larger scale, as well as we come down to the narrower, the site of interest. Okay, specific site. We use high resolution satellite data, and it is important that you, if possible, we try to visualize or see the terrain in 3 dimension. Okay, and that is the reason why we usually suggest that you use the stereo vision data. So nowadays we have Indian satellites which give some very high resolution data, that is Cartosat 1, and then later on also like you have more high resolution data which is coming up. So this helps you in generating three-dimensional picture of, or you can view the three-dimensional picture of that region. Okay, again the aerial view, it is not the ground uh, resolution. Okay, you're not looking at that. So because the identification of active fault scarp is important, and mainly, for example, I'll come to that point later. So, but usually what we look at is that the surface may be the same. For example, the surface was deposited 1,000 years old. Okay, and then there was a sort of an earthquake. So on a 2D image of this region, okay, what you will see is that you will see a sort of an same surface is continuing here. But in 2D image, this variation in elevation you will not be able to see. This change you will not be able to make out in 2D image. But in 3D image, the perception of elevation will be clearly seen. Okay. So for that reason, we usually advise to use the stereo vision photographs, okay, or satellite data. Trenching site identification is also important, as we discussed in the previous slide, that we need to classify the surfaces or the landforms as an older or younger. Okay, so we never go to trench the older landforms, because in the older landforms has moved twice. Okay, because it moved during when it existed, and plus at the when the younger surface also was been displaced. Okay, so more events, and you will have deeper faults, might be sitting deeper. Okay, because usually fault lies somewhere like this here. Okay, so if you are having older events, this will be covered mostly by the more colluvial material deposited here. So the cover of the sediments which are covering this fall will be deeper. So you need to dig go deeper in terms of excavation. So that is not advisable. Okay. So trenching site identification is also important. So mostly we try to identify the youngest displaced landform, and then we target the site for excavation, because the site will be like you will be opening the trench over here. Okay, so you need to be very careful about that, where exactly your fault is lying. Okay, so trenching to identify the pattern of deformation, or plus the past events, that how many times the earthquake has occurred along on this fault, detailed mapping of the exposed trench walls. So this part comes like we are talking about the exposed stratigraphy, exposed sediment succession in trench. Okay, and that we will study in detail, and we do mostly what we call the trench logging as well as mapping. So we map each and every layer, we log each and every layer. Then identification of event horizons. Okay, so what are the event horizon? We'll come to that also again. So any surface, for example, I'll just explain. We will talk later also. So any surface which existed, for example, this surface was there. Okay, so this surface existed and the fault was here, and after this there was a displacement. Okay, so this moved up. So this becomes your event horizon. Similarly, if after this, now there is a deposition here which occurs. Okay, and there is another layer which has been deposited. So, and if there is a next event, then that layer will become an event horizon. Okay, so how many events are there? This helps to identify based on the event horizons we identify in that. Then dating part of the event is important. Okay, because we need to have an age or timing of the earthquake. Okay, so the dating here, we follow different techniques. Okay, and then that will give you the age of the event. Okay, that is your earthquake event. So what we do is that we try to, of course, we try to date the event horizons. Okay, but at the same time, we also try to take the upper bound and the lower bound of the sediments. Okay, so that sedimentary layers mainly. So if there is, for example, there is a deformation here. Okay, so this was been displaced, and then you have this one, for example, here. Okay, so you have A here, you have A here, then you see B, or maybe you can, and then, for example, if we say that there is an, so this was like the was here, and then you have a sort of a cover of next event which is there, which was been deposited. Okay, so now to have the age of this event, what you see is that you have a sort of an capping of this. Okay, this is capped. So for example, this is your C unit, so this is capping and not displaced. Okay, so displacement was up to this only. Okay, so A and B were displaced, but C is the capping unit. Okay, so in this, the A which was on the top becomes the event horizon, and what we do is that we take an upper bound and lower bound. Okay, upper bound means that we take the youngest age from the A, youngest age, and the oldest age of C actually. So this we will be talking, but we usually use the upper bound and lower bound of to identify the, or bracket, which usually we will say that, of course, as I told, that we will date this also, but usually what we do, we try to bracket the event. Okay, so this we try to say that, okay, fine, the earthquake was occurred between this and this age. Okay, before present, and even we do sort of an calendar ages, we try to identify and all that. And then after doing this multiple events, if we come across in the trench, we try to prepare the chronology of the events. Okay, so we have like how many events have occurred and when those events have occurred. Okay. We also try to calculate the slip rate, because whenever there is a movement, there will be slip along the fault. Okay, so how many what was the individual or the slip during individual events. Okay, or the single event. Okay, we can say. So that also you can identify using this paleoseismic data. So anyway, now let us move further and try to see one by one that how what are these methods and all that. However, um, I would like to inform you right now that this exercise, there is a lab exercise we will be doing separately, and maybe we can release those videos in between the lectures, so that you can take up this. So these are the, this is one. So we'll be doing this one lab here, and then another lab what we are planning is to be done, and that will be sort of an and demo lab. Okay, of course, this will be we will be asking you to do, if possible, in we will give you the assignment in this. Okay, but if not, then at least it will be sort of a demo, and then whole lab lecture will be there, that how to process the data and what sort of data we are using, how to generate an anaglyph, and we will ask you to do some sort of in lab if possible. We will try. Okay, but another part which I'm trying to also will be a sort of a portion of the lab only, and that will be in field mapping part. Okay, So when we go to field, what instruments we use and all that. Of course, UAV, we will not be able to do that here. But another lab is the mapping part. Okay, so mapping in field. So this we usually use like total station, and plus we use RTK. So topographic profiling will try to like teach you people that how we do and what are the important, because height of any landform is extremely important when we are talking about the uplift rate, we are talking about the slip rate and all that. So this part plays an important role. Okay. Now, as I told that if you have what like high resolution 2D image also, okay, it is going to be difficult to identify the active fault because the young landforms are been displaced, and that is what we are looking at the quaternary. But still, I would say that paleoseismic studies and the active fault studies usually we try to confine within like Holocene. Okay, so Holocene landform is the youngest landform as we'll take a geological time scale. Okay. Now, if those landforms are like 500, 600 years old, then if they are displaced, you will not be able to pick up this elevation change, okay, in 2D images. Of course, if you are having the sun angle in that way where the photographs have been taken, then to some extent the shadow portion you will be able to say that okay, fine, there is an some sort of a shadow, so there will be an elevation change. This is in part of the photogeology. Okay, but otherwise, yes, you need to have an very like good expertise to differentiate between the younger landforms and the older landforms, and where exactly the landforms is getting terminated. Okay, so those things you will have to have the very good experience. Okay, but once you have the opportunity to see these images or the area in 3 dimension, okay, so this is a 2D image. Okay, I would say that this is, of course, this is an image, but this data is corona satellite photos. Okay, and this is data from US. Okay. So this was the data which was earlier available, and it was available in stereo. It was stereo vision capability, so you can. So usually this is again a separate domain of discussion. This is usually what they do is that they have an uh, forward image and after image. So forward image and after image, that means the satellite when it is like moving, okay, it will have 2 cameras. Okay, and so one camera, for example, if you are viewing this terrain, then this camera will scan this area, and when the satellite moves here, for example, okay, the other camera will scan this area. Okay, so the same area has been scanned by forward and after cameras. Okay, and this gives you a 3D of possibility of getting the 3D view, and these are what we call the stereo images. Okay, so 2D image, as I told, not this is difficult, of course, but it is for presentations and all that and illustration. It is fine. Okay, this again the corona satellite data, which is like almost it gives a resolution of 2.5 or maybe 3 to 2.5 meter of resolution. Okay, so this is very good data which is available. Now this data we have like for and it is freely available, not freely, but it is available. You can buy from USGS. Okay, so this is from of the Pinjore and Chandigarh area. The data, okay, old data, and this the advantages there of using this data is because this data is quite old, almost like I think 50 to 70 years old data is there, this one. Okay. So sometime it is important to look at the older photos, aerial photos or satellite data, because if you use this, then you see less modification of landforms. Okay. So this is one point that you can keep in mind. I will stop here and we'll continue in the next lecture with more details. Thank you so much. Namaskar.